Hello everyone, thank you for being here. In this video, I will be talking about our group's latest work, a software fault localization approach to explainable artificial intelligence. This work is a collaboration with graduate students Sunny Shree, Jaganmohan Chandrasekaran for the CSE Software Engineering Research Group, supervised by Dr. Jeff Lee. Machine learning models, the core of AI systems, perform tasks such as classification and prediction. But due to their black box nature, the user does not know how the decision came to be. AI systems are quickly becoming ubiquitous and can be found integrated in autonomous vehicles, medical imaging equipment, and even human decision-making applications. We can consider a bank loan application, which uses machine learning to accept or deny applicants. An explanation may be useful to a rejected applicant to help them change the outcome. Explainable artificial intelligence, or XAI, is a subfield of AI in which we aim to generate explanations that can help better understand a model's behavior, improve the trust, and assist in debugging a machine learning model. We identify a connection between the fault localization problem in software engineering and explainable artificial intelligence. In software, given a failing test case, a software engineer identifies which part of the input caused the failure. In XAI, given a decision made by a model, the objective is to identify the features that influence the decision. We propose a software fault localization approach called delta debugging to create an explainable artificial intelligence tool for explaining image-based models. We evaluate our approach on an open source model trained on the MNIST handwritten digits dataset. In our approach, we aim to generate two explanations, counterfactuals and semifactuals. Counterfactuals are of the form, if X had not occurred, then event Y would not have happened. If we take our bank loan example, because your income was below $45,000, the loan algorithm could not recommend that you receive a loan. On the other hand, we have semifactuals. Even if X had not occurred, event Y would still have happened. So even if your income was above $30,000, the loan algorithm could still not recommend that you receive a loan. We propose a delta debugging algorithm to minimize the failure-inducing test case. Our approach can be best understood with an example. Here we have our original image, a handwritten digit, with a classification of 2. And we will walk through how the tool generates a semifactual explanation. In the first phase of our algorithm, the image is segmented into 80 pieces. These segments become the initial failing test cases, and the passing test cases are the empty set. We aim to minimize the failing test case while maximizing the passing. For the delta debugging engine to work, an initial set of deltas must be passed. This is the difference between the failing and passing test cases. The DD algorithm is an iterative process and will continue to run until the one minimal failure-inducing difference is found. So here we have a snapshot view of the internals of the algorithm. You can see that the prediction here on the new image that was generated has changed, so it is a 1. If you recall, a semifactual is of the form, even if X had changed, Y would not have changed. So here, this does not pass the requirements for a semifactual, so we will continue to run until we reach that one minimal solution. Applying the most changes possible without crossing the prediction boundary is a semifactual classification. We can see on the right that this image has a little bit more pixels to it, and the prediction is still 2, compared to the one that we showed in the previous slide, where the prediction had changed to 1. Contrastively, applying the least number of changes in order to cross the boundary is a counterfactual classification. To evaluate our approach and experiment, we use an open source model trained on the MNIST dataset. To generate explanations, we use 80 randomly selected images from the test data, 8 from each class, 0 through 9, with the original image, segmentations, and initial deltas. And we iteratively run the 2 following tests. Test 1 will be used to create semifactual explanations, and test 2 will be used to create counterfactual explanations. The full results and tool demonstration can be found online in a shared Dropbox. 67 out of 80 semi-factual explanations were generated, and 56 out of 80 counterfactual explanations were generated. Please see the full results for a full comparison and evaluation. Future work includes extending this approach to work with tabular or text data and utilizing explanations to improve AI systems. There are still other areas to explore regarding ethics and biases of machine learning models. Thank you.